Atomic size. We're going to look at some periodic trends that we can find on the periodic table, and one of them is the size of atoms. And so these trends are useful because just by looking at positions on periodic table, we can kind of predict, oh, well, this one's probably bigger than that one. They're not hard and fast rules, though there's exceptions, and so they're just kind of generalizations. But in order to talk about atomic size, we have to be clear on what exactly are we talking about. Atomic size can be defined in different ways, and you would use the different definitions in different situations. The non-bonding atomic radius, also called the van der Waals radius, would be measured in an atomic solid, such as krypton. So for some atoms, you can't really get the non-bonding radius because they don't form atomic solids. But for krypton, we can measure the distance between the two nuclei. And then we're going to assume that the radius of the atom is half that distance. As you think about how do you measure the size of an atom? What's the outer part of the atom made up of? Standing waves of electrons, right? It's not really anything that you could put a ruler on or anything. So we look at the atoms in a solid and see, well, how close are they to each other? And then we're just going to assume that they're basically touching each other like this. And so it's half the distance between the two nuclei. We can also look at a bonding radius. So if we look at a bromine molecule, we can identify the distance between the two nuclei. And we can say, well, we'll call the radius half of that. This is going to be shorter, though, because the bond pulls the atoms in. And they're not hard spheres like marbles. They're more like, a spongy ball or something. And so when you put them together, they can kind of deform and squish into each other. So for nonmetals, we look at two atoms bonded together. In metals, we look at the distance between atoms next to each other in a crystal of the metal. When we just say atomic radius, this is a more general term, which is sort of combining things like the van der Waals radius and the bonding radius and kind of averaging them together. So looking at measurements from a large number of elements and compounds. And this is what we're going to talk about when we talk about size of atoms. And we can estimate approximate bond lengths by looking at the sum of the atomic radii of the bonded atoms. So if you have a carbon atom bonded to a hydrogen atom, we can approximate that bond length by saying, well, let's add the two radii together. So now we can get to the trend. There are two trends. There's one going down a group and one going across a period. If we look here, this is a graph of atomic radius in picometers as a function of atomic number. So as we go across in this graph, the atoms are getting larger and larger in terms of numbers of protons. But we see that their atomic size goes up and comes down and goes up and comes down. So if we're looking at the peak here, lithium, sodium, potassium, rubidium, cesium. These are the alkali metals. They're all in group 1A, right? And so looking at these guys, we're looking at the trend as we go down a period, and what's happening? They're getting larger, right? So as you go down a group, the atoms get larger in size. And you might say, well, duh. You've got more protons, more electrons. Of course they're going to get larger. That makes sense. Then there's another trend. Let's look sodium, and next to sodium is magnesium, and then boron and carbon and nitrogen and oxygen and chlorine and argon. And here what we see is that the radius decreases as we go across a period. And that does not make sense intuitively, because argon has more protons and electrons than sodium does, and yet it's smaller. But there's reasons behind this. So here's another way to look at it. Here, the height of each of these blocks represents the radius. So here's sodium, magnesium, and they're getting smaller as we go across. The reason for this trend has to do with shielding and with effective nuclear charge. We talked about a little bit before. So we've got outer electrons, the valence electrons, and we have core electrons. The core electrons shield the outer electrons, and so they don't experience the full strength of the nuclear charge. Here looking at lithium. Lithium has a +3 charge on its nucleus. There are 2 core electrons in the 1s orbital, and those are going to be closer to the nucleus, and they shield this 2s electron, the valence electron, from the charge. And so this electron is really only seeing a +1 charge. The force of attraction, the potential energy in the attraction between oppositely charged things depends on the charges. So if we take this from a 3+ and make it effectively only a 1+, it's not as attracted. So we say that the effective nuclear charge is the net charge that is experienced by an electron. You can make a math equation of it this way. The effective nuclear charge is the actual nuclear charge, the atomic number, the number of protons, minus the shielding. And so that's the number of core electrons. And so this effective nuclear charge is often going to be the same as the number of valence electrons. Let's look at nitrogen and argon as examples. Actually, I'm going to change that. I'm going to look at nitrogen and neon. So we're not going to do argon, we're going to do neon. So for nitrogen, what is the atomic number for nitrogen? 7. So it has 7 protons in the nucleus. How many electrons does an atom of nitrogen have? 7. And how many of those are valence electrons? 5. It's got 5 valence electrons. We know that because it's in group 5. So if it has 7 total electrons and 5 valence electrons, it must have 2 core electrons. So the effective nuclear charge is the atomic number minus the number of core electrons. So the effective nuclear charge is +5. Any questions about that? I'll take that as a no. What's the atomic number for neon? 10. So it has 10 protons in its nucleus, 10 electrons total. How many valence electrons? 8. So 8 valence electrons. And how many core electrons? 2. So we're going to take that the actual nuclear charge and subtract the number of core electrons. And so we get an effective nuclear charge of +8. So what this tells us is the valence electrons for nitrogen are experiencing a +5 charge from that nucleus. The valence electrons for neon are experiencing a +8 charge. It pulls it in. The force of attraction is greater, and so the electrons get pulled in a little bit. It's the electrons in their orbitals that make up most of the volume of our atom, and so that affects the size. So as we go down a column, we are adding electrons in a higher principal quantum number, right? So the valence electrons for sodium are in n equals 3. And for potassium, they're in n equals 4. As n, that principal quantum number, increases, the size of the orbitals get larger. And so the atoms are getting larger. When we go across a period, yes, we're adding protons and electrons to make larger, in terms of numbers of, or in terms of mass, atoms, but the effective nuclear charge is increasing, while n, that highest principal energy level, is remaining the same. Nitrogen and neon both have their valence electrons in the second level. And so the second level is roughly the same distance, but then that effective nuclear charge pulls those electrons in and it gets smaller. These trends are things that we need to be able to remember for an exam. And you've got this up, down, right, left, greater, smaller thing going on. If you don't remember the reason, if you can't think through the reason, it's really hard to remember the trend. In the transition metals, we see less predictability, which is generally how those transition metals are. As we go down in a group, we still see increases in size, but as we go across, there's much less difference. Here we go, much less difference than across the main group elements. And that's because the valence shell is NS2. It's not the d electrons, it's the s electrons. And so adding more of those d electrons is not really going to mess with the size. The effective nuclear change is approximately the same. So if we go back to this, maybe let's look at this one. So in here we have the period 4 transition elements and the period 5. And so we see some decrease as we go across, but then it levels out and actually increases a little bit at the end. And so they're not very predictable. The trend with the main group, in this row here we have just main group elements, and it's a much nicer trend. If we discount these green ones and just look at the main group elements, they follow a consistent trend. It's not linear, but it is a trend. So we should be able to answer questions like this. On the basis of periodic trends, choose the larger atom in each pair, if possible. Well, tin or iodine. We need to look at their positions in the periodic table. So I'm going to just draw a little section of periodic table for you. Tin would be here, and iodine would be over here. So they're in the same period. Which is larger, the one on the far right or the one on the far left? The one on the left. The tin is larger. The effective nuclear charge on iodine is greater, and that pulls the electrons in, and so it makes it smaller. As we go across a period from left to right, the atoms get smaller. So tin is larger than iodine. How about germanium or polonium? You gotta find these guys. So here's germanium, and here's polonium. So comparing these going across, which one is larger? Germanium is predicted to be larger. Looking at the trend going down, which one's predicted to be larger? The polonium. So the trends are opposing each other. What do we do? Well, it does say, if possible. So we might want to say, not possible.
Could you calculate the Z effective?
Could you calculate the Z effective? You could calculate that, but because we're looking at valence electrons in different shells, different levels, that's not really going to help. So not possible, I think, is an entirely valid answer. What if you're forced to pick an answer? Sometimes on a multiple choice exam, you have to pick an answer, right? I think in general, the trend down a column is more significant than across a period because we're adding. The valence electrons for polonium are 2 quantum numbers higher than for germanium. Okay, and yeah, we've got a little difference in effective nuclear charge, but if I had to bet, I'd say that the germanium is smaller and the polonium is bigger. So if forced to choose, I'd choose polonium. How about chromium or tungsten? So they're vertical, chromium and tungsten. Which one's bigger? The tungsten, the one on the bottom. Okay? Any questions?